to do that. But with that, it also, I wanted to just say that my understanding is that you have had a number of talks on FRBs in the last 6 months to a year. So I decided that I'm going to skip all the introductory part, including some fascinating history of these objects, because you probably have heard it more than once. So for the sake of efficiency, I am going to skip all of that. Observations, I will mention very briefly. And roughly speaking, 2/3 of my talk will be on the physics of it, the physics of FRB, the radiation mechanism. And then the last 1/3 will be on cosmology, FRB cosmology. So that's another thing that, CITA has got such a strong, not only presence, but such a strong, powerful group with cosmology that I was hoping that I would have a chance to kind of discuss more critically what FRBs can do on all of these different things, radiation to cosmology. But with that, let me get right to it. And I will jump kind of with the galactic FRB that you all know very well about, that was discovered April 28 of last year. And we know this was observed by the STARE, the Caltech telescopes, and also the Canadian CHIME. We know that this is associated with a known magnetar, with a known source, which is soft gamma ray repeater source. The property of this object is summarized here in this slide. And I will mention just a few things here that I would just highlight and mention. So the magnetar field strength for this object is about 2 times 10 to the power 14 Gauss. The spin period of the neutron star is 3.2 seconds. P over P dot, rough estimate of the age of the system is about 4,000 years. CHIME saw 2 pulses from this outburst in the radio band, and they are separated by 30 milliseconds. Useful piece of information that I would make use of in the development of the model and the story. The only other piece of information that I just want to draw your attention to is the energy in the radio band and the X-ray band. So the energy in the radio band that was released is 10 to the power 35, and in the X-ray band, about 4,000 times larger amount of energy came out in the X-ray band. And now, this is more or less all that I am going to be telling about the observations, except as needed as in the terms of looking at different clues and different information that we need to draw and make use of. So, brief summary of the observed properties of FRBs as a FRB population. So we see burst with duration between 1 millisecond and 20 milliseconds. And so the duration itself suggests, without any calculations, without anything, that the underlying object producing this outburst is neutron star or a stellar mass black hole. That's the natural time scale. The flux varies in the radio band on a time scale of 10 microsecond, maybe sometimes a little smaller, sometimes a little larger. I will share some more data about it. But the variability time, we know that the size of the source should be the size of the source, as in the source that is producing the radio emission. That size should be order of no larger than C times 10 microsecond and times the Lorentz factor of the source moving toward us. So that means about 1 kilometer times the Lorentz factor gamma. That's the size of the source. It's a compact source, energetics. Here I just draw your attention to one particular object, The first one that was spotted in the terms of identified, and the one which is a prolific repeater, the FRB 121102, the amount of energy released in the radio band in the 6 years is order of a few times 10 to the power 43 erg. Now, if this energy were to ultimately come from the magnetic field or the dissipation of magnetic field with 100% efficiency, then the strength of the magnetic field should be 10 to the power 13 Gauss or larger. And that's with 100% efficiency. However, if the efficiency of converting the energy to the radio band is smaller than 1, so taking this example of the galactic FRB, where more than 10,000 times more energy came out in the X-ray. So if we were to take that as the efficiency of converting energy to the radio band, then the requirement on the magnetic field for this repeater will be 100 times larger. So the field strength associated with this object will be greater than 10 to the power 15 Gauss. Very simple energetic argument. The progenitor. 9 FRBs have been localized. We know they are at shift, and we also know we have good evidence that the contribution to the DM, just in case anybody doesn't know, have never heard of DM in the audience, I doubt it. DM, dispersion measure, or the electron column density between the source and us. That's coming from the host galaxy of the FRB. It seems small. It's not a large contribution to the DM from the host galaxy. And therefore, most FRBs are not associated with very young supernova, remnant, or dense regions of the interstellar medium. I am going to get to the radiation mechanism now with that. And so I just want to point out an obvious thing that you all know, and that is that the FRB radiation, if it were to be incoherent radiation, like the stellar light or the AGN, then the brightness temperature, the brightness of the source needed to produce the flux that we see in the radio band is 10 to the power 35 Kelvin, clearly unphysical, clearly means that the emission is not coherent. This radiation is coherent, which simply means that different particles in the source are radiating in phase. The electric field is adding up in phase. The flux or the luminosity goes up as the number of particles is squared. Very basic point, making it in case there is a person in the audience who has never seen this before.
So Pawan, I have a question.
Please do.
So in principle, another way to get around this upper limit on the temperature and without coherent emission is with relativistic motion. So do we know if we can rule this out for fast radio bursts?
Very, very, very much so. So you are right that relativistic motion buys something, meaning it makes the requirement that it reduces the brightness temperature, TB, but by a factor of gamma in the appropriate way of looking at it. So you can reduce it, but if you have gamma of a million, the Lorentz factor of the source is a million, you still are left with a very high brightness temperature, which is still very unphysical. So the answer is it cannot. There is no physical way to make relativistic motion bring down the brightness temperature to make it physical. So it cannot.
I see. Thank you.
Many FRB mechanisms have been proposed. They fall broadly in two categories. And they are that the radiation is produced, this coherent radiation is produced within the magnetosphere of the magnetar, shown here, this on the right-hand side. And I would call that the near field model. And the other possibility is that what we have is that there is an outburst, and in that outburst at the surface of the magnetar, there is a relativistic outflow where this outflow is moving with Lorentz factor, which is high, whatever it is, few tens, hundreds, thousands, and transporting the energy via this outflow, via this jet, to large distances, well outside the light cylinder, to a radius between 10 to the power 9 centimeter to 10 to the power 14 centimeter. And at this large distance, the kinetic energy and possibly the magnetic, the pointing energy in this jet is dissipated and then converted, some fraction of that is converted to coherent radio emission. So that's another class of model. So I would call that faraway model. So near field model and faraway model. These are the two broad category of possibility regarding how the radiation is produced. And for this latter model, the faraway model, very nice work has been done extensively by people at Columbia, Brian Mesker, Lorenzo Cironi, and so on. Okay. So the point that would wish to make with this particular slide is that you may have heard about the fable of blind men and an elephant. So the point that I wish to make with this slide is that if you look at, so FRBs is a complex process. And if you simply look at one piece of the clue, well, you can come to some conclusion, but you would be missing the big picture. So what we need to do is make use of all the clues that we have got to decide and determine how nature produces FRP. So it's like a jigsaw puzzle, and we have got data, meaning different pieces, and we need to put all these pieces together to see the big picture. And that's what I wish to convey and do in the next about 20 minutes. So with that in mind, what I'm going to do is take these different pieces, and I'll let you know there are 6 different pieces, all driven by the data, concrete, nice data, collected by probably many of you in the audience here, and then try to piece it together and see what that is telling us about the FRB physics and how the FRBs are produced. Clue number 1. Light curve is variable. The variability time for this particular burst that you see here and the data is 20 microseconds. This burst lasted for 20 times longer. So the burst lasted for 0.4 millisecond, and you can see the light curve vary, and that is quantified here, 20 microseconds. Now that is not the only case. We have other cases where we see burst vary on time scales of similar order, 10 microsecond, less or a little bit more. Let's try to understand, and we will try to understand the variability time, but I think the more interesting thing is the duration of the burst is much longer than the variability time. That's the clue, that's the piece of information which is very useful. So let's consider in a very general sense that there is a source. The source which is producing the radio photon, coherent radio photon, is moving with a Lorentz factor gamma toward us. And it is producing the radiation when the radius of curvature of the source or the distance of the source from the central object, magnetar, is r. There are 2 time scales. One is the duration, activity duration of the central object. That's TACT, the activity time scale. The duration over which this burst or the explosion lasts at the surface. Then the second time scale is the curvature time scale, which is PR, that is the radius of curvature, divided by 2c, gamma is the Lorentz factor of the source moving toward us, Now, this time scale is very simple to understand, partly relativistic beaming. Photons are all beamed within an angle of 1 over gamma. So which means that we only see a small patch of this shell. Even if it were to be a spherical shell moving toward us, we only see a patch of angular size 1 over gamma, of physical size r over gamma. That's all we see. And so this time scale is nothing but the time scale, the time, the difference in the arrival time of the. Wiley, do you have something here? Wiley? Okay.
No, sorry.
No. Okay. So the time is, this curvature time is the time difference in the arrival of photons from this along the line of sight versus the photon which is arriving from an angle 1 over gamma from here. So the pointer that I'm putting at, yeah? So which means that there is an averaging. So when we see photon at one instant in time in the observer frame, that is being averaged over this entire surface, right? So which means that any fluctuation which is on a time scale is smaller than the curvature time, that's wiped out. So there is a variability time. The shortest variability time is given by the curvature time. That's the point here. For the faraway model, in a very broad sense, one can prove, almost like a theorem, that the curvature time is the same as the duration of the burst, which means that the ratio of the variability time to the duration of the burst is order unity. It can be half, but it can't be 0.1. For the near field model, when the burst, the coherent emission is produced close to in the magnetosphere of the neutron star, this variability time can be and is much shorter. So if the burst is produced, as an example, at a radius of 10 to the power 8 centimeter from the source, which has a Lorentz factor of 100, then the curvature time scale is 0.2 microsecond. And so in principle, one can have the light curve vary on a very short time scale. In other words, one can have the duration of the burst divided by the variability time to be a large number, 10, 100, maybe even 1,000. That in principle is possible. So you see the clue number 1 is already with this very simple physics consideration is providing one piece of the jigsaw puzzle. So let's keep that in mind. And let's ask, is it possible that in the faraway model, we can produce a burst with much shorter variability time? And the answer is that yes, one can in the following way. This is R over gamma patch of the surface that we can see due to the special relativistic beaming of the photons. Okay, but what if not the entire surface is radiating, but only a small patch shown here is producing the coherent radiation? And the size of the coherent patch, the size of these patches is zeta times R over gamma. Yeah, so a small patch is producing it. In that case, the variability time can be very short. It would be zeta times, where zeta is a number much less than 1, times the duration of the burst. So now this is a scenario where a small patch of the surface that we can see is producing the coherent radiation. It can have a variability time much, much shorter than the duration of the burst. But it comes at a cost. It is reducing because of the fact that only a small section of the surface that we can see is radiating coherent radiation. The efficiency is down. The efficiency is reduced by a factor of 1 over zeta squared. Let's take a case, the one that I showed you, where the burst variability time was 20 microsecond, the duration is 2 milliseconds, Therefore, we are looking at the requirement on zeta is 1 over 100. The efficiency will go down by a factor of 10,000. So for the external shock, the faraway model, the natural efficiency is 10 to the power minus 4 or 10 to the power minus 5. That is further reduced in order to explain the variability. The efficiency becomes 10 to the power minus 9. Now that's just not physical in the terms of the energy requirement. Let's keep that in mind.
So I want to have another question
Of
about the
course.
Apache model.
Yes.
So if I remember correctly, some FRBs at least are very highly polarized. And a priori, I would assume that these patches, is there any reason to assume that each one of these patches, that all these patches would have the same polarization? Because
Yes.
otherwise they would cancel each other out.
That's right. There's a very good reason to believe that they would have nearly the same polarization angle. It is not completely a generic, meaning broad blanket statement, but for a wide class of models, the way the coherent radiation is produced is that particles upstream, electrons and positrons, upstream of this relativistic source, when they cross the shock front, they gyrate with the magnetic field. So upstream medium is magnetized, and that field, upstream magnetic field, is coming from the central source, which means that the magnetic field is parallel magnetic field, and the length scale of the magnetic field over which it's coherent is much larger than R over gamma. And therefore, and the polarization in the terms of the electric field of the photon that is being produced, that electric field will be perpendicular to this large scale upstream magnetic field. So you see the polarization angle from different patches would be nearly parallel, very nearly parallel. So that's the reason.
Thanks.
Please let me know if that is unclear or if you have a follow-up question. All right. So I have, as I go along in this talk, I am going to have many places where I say, these are the things that as a theorist would be very useful to have from observers. So this is the first such slide to quantify. So those of you in the audience who are observers, I suggest, please pay some attention to it. And I would be, of course, very happy to answer your questions, elaborate, discuss further. So these are hopefully things which are not terribly difficult to measure. They are not straightforward because of scintillation. So one has to be very careful, but this is doable and would provide very useful information regarding the physics of FRBs. Let's go to clue number 2, spectral properties. Many FRBs show emission in a narrow band, delta nu over nu less than 1. This is an extreme case that I share with you. This is an extreme example of a S-cap burst where the emission, I don't know if you can see it, but I am this putting my pointer here, pointer circling this, that this is the emission. The emission is seen in a narrow band of 65 megahertz at a frequency of 1.4 gigahertz. The rest of it is just noise, nothing. The only is this bright patch, right? Very narrow emission. But as I say, this is an extreme case. There are many cases where we see emission in a narrow band. So this is a collage of the chime burst. And what I wish to point out is that, so many, I'm assuming that all of you have seen diagrams like this numerous times. If not, you will stop and ask me what this diagram is. So otherwise, I'm just going to proceed. I want to draw your attention to that emission here you see is in in a relatively narrow frequency band. No emission here at lower frequencies that I have highlighted here, no emission at the lower frequencies, just cut off at some frequency, and below certain frequency, no emission, right? It goes in the other direction too. No radiation, well, radiation at low frequency, lower part of the chime, but nothing at high frequencies. Many examples of that. But I'm drawing your attention to these cases where there is a low frequency cutoff of the flux. That provides interesting clue. We see that also in the galactic FRB, that there is a cutoff for the second pulse, no emissions seen below about 500 megahertz, right? Now, the very interesting thing, and the reason I want to draw your attention to, is that for some cases, you can invoke scintillation. You can say that we don't see flux in a certain frequency band because of scintillation in the interstellar medium, right? Either of the Milky Way or the host galaxy of the FRB. Now, this is one case where I think, and we have made a strong argument that scintillation cannot quench this flux here, because we have two pulses separated by 30 milliseconds. From pulse number 1, we see this emission at the low frequencies, none at the high frequencies, low frequency. Here is the opposite, no radiation seen at low frequency. And it is very difficult, if not impossible, to have scintillation change on a time scale of 30 milliseconds, right? Let me emphasize, it's not impossible. You can cook up a model to do that, but that would require really fine tuning to be able to do that. It's not easy sell, it's not easy go, okay? So this is an example where you can't get away by saying scintillation is quenching the flux at lower frequencies. Let me describe why this is a very interesting clue. The reason it's very interesting clue is tied to basic physics. And the basic physics is this. This is again a source that is moving toward the observer with Lorentz factor of gamma. So we see a patch of the surface of angular size 1/gamma, the relativistic beaming of the photons. Furthermore, the Doppler factor is angle dependent, because directly along the line of sight, we get the full Doppler boost, which is a factor of 2gamma. But at some angle, non-zero angle, the Doppler boost is given by this expression, and the Doppler boost becomes smaller as the angle theta increases. So which means that photons are boosted, their frequency is boosted by less and less as we go away from the line of sight. That is to say, away from the velocity vector pointing directly in our direction, right? So let's keep that in mind. And of course, most of the photons are beamed, and we see are within this angle of 1/gamma. However, we can see also photons from an angle larger than 1/gamma, where consider this part of the source, which lies outside of 1/gamma. So from this part of the source, most of the photons are beamed in a cone of angle 1/gamma. And since this patch here is at an angle which is greater than 1/gamma from our line of sight, so this cone is pointing away from us. So we will see most of the photons will not reach us, but a small fraction of the photons from this larger angle theta will arrive at the observer, but they would be Doppler boosted by a smaller factor. So we will see lower frequency photon arriving a little bit later from angles greater than 1/gamma. That means this very simple physical consideration tells us that it's impossible to simply turn off the emission below a certain frequency. You can't do that. The flux can't be sharply turned off below any frequency. The fastest decrease in the frequency at low frequencies is going to be no faster than nu squared, as long as the angular size of the source is larger than 1 over gamma. Right? So that's another clue. Again, another thing for the observers to pursue, to see how generic this is. Clue number 3. And that is closely spaced pulses. The galactic FRB was a very nice example where we saw 2 pulses separated by 30 milliseconds. But there are many cases like that. We have seen pulses arrive from the same object separated by 30 milliseconds. There is wealth of data for 121102. Okay, so what does that teach us? Why is this an interesting clue? The answer is that if you have a faraway source where there is relativistic moving outflow is interacting with the circumstellar medium, there is a shock, electrons and positrons are heated up. The cooling time for this thing is order of second, right? So to have 2 pulses separated by 30 milliseconds, the second shock is going into the medium, which is already heated up. But even if you find some way of cooling of the medium, you still need to arrange, fine tune to produce 2 closely separated pulses that we see, because you see there are 2 pulses that we see separated by 30 milliseconds, but they are produced at a radius of an AU. And AU means 1,000 seconds, light travel seconds apart in the terms of the physical distance from the central source. So they are produced 1,000 seconds away and coming together within 30 milliseconds. So that poses very severe restriction as to the property of the upstream medium, upstream of this outflow, or upstream of the shock. To complete this case of the galactic FRB, the 2 pulses that we saw, the upstream medium for pulse number 1 should have a Lorentz factor of order few. The kinetic energy luminosity of the upstream medium, wind medium, should be order of 10 to the power 36 arc per second. For the second pulse to arrive at a gigahertz frequency, the upstream medium should be moving with a Lorentz factor of 100, and the kinetic energy of the upstream unshocked medium should be 3 to 4 orders of magnitude larger. Now you say, so what's the big deal? The big deal here is the following. These diagonal lines that you see, let me go back. The diagonal lines that you see, they are lines showing the frequency of the coherent radiation from this shock. So if the upstream medium were to be just slightly different, the emission will come out at a very different frequencies. Instead of a gigahertz or half a gigahertz, it would be at tens of gigahertz or below 100 megahertz. That's the problem. So there is a very fine tuning needed to produce 2 pulses separated by a small time, 30 millisecond time. Clue number 4. Clue number 4 is, again, basic physics. And this is basic physics of radiation pressure physics. And here is the way it is different for the coherent radio of the FRB emission. For standard Thomson scattering, a photon is scattered by a photon with a Thomson scattering cross section. But that's assuming that the photon is scattered into a quantum state which is unoccupied. Okay? However, the occupation number of each quantum state for the FRB emission is huge. the occupation number for each quantum state is 10 to the 37, right? So photons being bosons, the cross section is enhanced. Particles want to scatter into a state which is already occupied. Okay, so that leads to a huge enhancement in the scattering probability. Now there is a inverse process of photons getting scattered from this final state to the initial state. Because of this fine cancellation, the enhancement to the probability is much smaller than 10 to the 37, but it is still, the cross section is still enhanced over the Thomson cross section by a factor of 1 billion at a distance of AU from the source. Now that has a consequence that there is this enormous radiation pressure that will be there in the source that is trying to produce this intense radiation, right? And so the only two ways that the source can withstand this enormous radiation pressure, this enhanced radiation pressure, is one, produce the coherent radiation at a distance larger than a AU, so that the photon beam size is small, and therefore the probability of scattering into an occupied state is correspondingly small. That's one way of doing it. The other way of doing it is that you do it close to the magnetar surface, where the magnetic field strength is large, and therefore the Thomson cross-section is suppressed by a factor of the cyclotron frequency to the FRB, the radio photon frequency squared. And that's a large suppression factor close in. So those are the two ways that you can do it. There was a recent discovery announced by LOFAR at 150 megahertz that makes this particular constant that I mentioned even stronger. Okay. Point of all of these clues now putting together is that it's very hard to produce FRB radiation between 1,000 kilometers and an AU. You either do it close to the surface of the magnetar or do it far away. Clue number 5. We have the X-ray from one source, that's the galactic FRB. The width of the X-ray is the width of the X-ray spike is 5 milliseconds. The width of the radio emission is 0.6 millisecond, so a factor of 10 smaller. Furthermore, the X-ray spike came, the X-ray photons came, especially the hard X-ray photon came with a little bit of a delay with respect to the radio photon by 5 milliseconds. In the faraway model, it's just not possible to do it. They will be concurrent. And the duration of the X-ray spike should be comparable to the radio duration. There is no way that you can make this thing a factor of 10 larger in the X-ray band. So with that, that's another piece of clue. And the final piece of the clue to this jigsaw puzzle, or that, is polarization. And this is a topic of another talk, but the point here is the following, that there are bursts where we see very high degree of polarization, and there are cases where we see the polarization angles change over the duration of the radio burst. And these are some examples of one particular burst where you see the polarization angle change. And that's such a reminder of what we see for the radio pulsars, this swing. And the origin of that is that we have an emission that is produced in the magnetosphere of the pulsar. And what we are looking is the sweep of the magnetic field direction, producing this change in the polarization angle. So we have these clues. So let's put it all together. What we have got, putting all these pieces, is synthesizing all in this one slide. Short variability time, 10 microseconds, suggests that the radiation is produced in a small region of size about a kilometer or less. not far away from the neutron star.
Pawan?
Missing frequency. I heard someone.
Yeah, that's me. Do you mind
Please
if I
go
ask?
ahead.
Yeah. So really quickly on the last slide, it shows that for an individual burst duration, you have a significant change in the linear polarization angle.
Angle,
But-
yes.
But it also looks like if you look at the y-axis,
Yes.
between bursts, there's also a change in position angle between bursts, individual bursts. Is that also real? Just
I am looking at it with you here, and I think that may also be the case.
Okay.
I think it is real. I think it is real.
Okay, thank you. That was my question.
So synthesis of all of these things suggests closed-end source that should be able to withstand this is strong enhanced radiation pressure. So one model is, and it seems very natural to me, certainly personally it seems very natural to me, is that what you do is that there is a magnetic disturbance and the Alfven wave energy is converted to coherent radio emission. And that's the model that I would talk about. And I am going to be looking at the time here. So let me describe this model. There is some disturbance in the crust. It could be in the form of a shear wave, but it doesn't have to be a shear wave. It could be some fault. It could be some trigger that starts, propagates along the surface. And what it does is that it shakes up the magnetosphere. And where the magnetic field lines are shook in this closed field line region, that produces a trapped file ball. That's the story. That's the standard model of Thomson and Duncan for the soft gamma ray repeater. But this disturbance along the open field lines, that disturbance travels to larger distances and wave becomes charge star. And then electric field develops, and a strong electric field then accelerates electrons and positrons, and they move along the curved field lines and have curvature radiation. And that's the model that I will describe in a little bit more detail. And then what I would do is that I would like to turn to cosmology. There are many people in the audience who do cosmology, so I would like to have a chance to describe that work and also get some, hopefully, input and feedback on that.
Can I ask a quick question?
Of course, yes.
So in your little cartoon with your Alfven waves traveling out, it seems like you essentially have some sort of beaming. And my question essentially is whether this implies that we should also see something like a slow radio burst for angles, outside the beaming angle when you're looking at a little bit off axis.
So there is a suggestion that has been made very much what you say. There is a paper that was posted a few weeks ago on the archive making just that point. So I would say, yeah, I think that is it. Yeah.
Well, I guess my question, I guess, is whether you could essentially use that. I don't know anything so much about the radio instrumentation, but you could use the presence or absence of these slower radio bursts to constrain the beaming and know whether this basic cartoon model is correct. So do we know if there is any evidence for these things, or?
Okay, so it's a little tricky. So if you're outside of the beam, also you recall from one of the earlier slides that I showed, the Doppler boost factor would also be small when you're outside of this 1/gamma cone, yeah? So which means that you will see radiation, right, at a lower frequencies, lasting for a little longer and much fainter, because most of the photons are beamed in a direction away from us. Remember that relativistic beaming factor? I mean, I'm just,
Yeah.
So the answer is yes, what you say is true, but it would be a faint, much fainter signal and harder to detect. But yes, there.
Okay,
Most
thank you.
definitely answer is the physics dictates that it ought to be there. Right? Okay, so question is, how does the curvature radiation work? Coherent curvature radiation work? The answer to my mind is that associated with the Alfven wave, and you see this disturbance along the open field lines, these Biggles-Alfven waves, there is a current associated with the Alfven wave along the magnetic field direction. That current is carried by electrons and positrons, which are moving in opposite direction. And so this is the classic two-stream instability that they are subject to. The two-stream instability operates on the plasma time scale, which is nanosecond. So you will have clumps form on a nanosecond time scale. And then once you are in the wave is in the charge starvation zone, then what happens is that these clumps, which are electrons and positrons, they are pulled apart by the electric field, and then they follow the curved magnetic field lines. And so that's how this thing comes about. There was a suggestion by Chang et al. That maybe Alfven waves can carry the charged particles, advect the charged particles, and therefore doesn't become charge starved. It's an interesting idea, interesting paper, recently posted to the archive. And there are certain points here which are attractive. The bottom line is that Alfven wave requires a certain minimum column density of electrons and positron to prevent charge starvation, and that requirement is 10 to the power 20 particle, which means nothing to most of you who don't work in the subject, but that is something on the order of 100,000 times larger than the Goldreich-Julian density. And this is assuming that there is a 100% efficiency for converting Alfven waves to the coherent radio emission. In practice, not true. And so you will need something on the order of million times the Goldreich-Julian particle density to prevent charge starvation. Let me skip this thing. I am going to go to
Pawan.
Yes, please.
Hi.
Yes, Chris, please.
So of
please,
course,
Chris.
there is the phenomenon of pulsed radio emission from magnetars, which can be quite bursty. And
Yes.
I think it's fair to say that the detected bursts from 1935, it's conceivable they're produced by the same mechanism that produces the pulsed emission from galactic magnetars, but scaled up in some way. So, you know, there has been some thought given to how the pulse radio emission is produced, since it's quite distinctive from that of ordinary radio pulsars. Of course, it's much brighter at high frequencies, right? They're the brightest pulsars in the sky at 100 gigahertz or above, and also quite stochastic. So one thing you do get in the magnetars in the quiescent states is some mismatch in currents near the boundary of the co-rotating magnetosphere, which can then drive reconnection.
That's right.
And the suggestion that I made was that that in order to heat up plasma, then you get a sort of cascade process from large scales to small. And you get charge starvation, not by a geometric effect, but by a rise in the current density due to nonlinear wave couplings. Anyway, so potentially
yes,
that sort of thing could be going on at some level in some subset of FRBs. But
of course, yes, Chris, of course. Good point. Good point. And yeah, sure, that's a possibility. As I say, I am trying to kind of convey a generic story. Yeah. A generic story. There is a magnetic disturbance, right? And that you run out of charges. I mean, that generic story and the details of it, how it exactly happens, I mean, we don't know. At least I don't know, Chris. And so that is something, there could be many ways that is possible. And yeah, I am very much looking forward to talking with you more about it. And yeah, so with that, is there, should we, would you like for us to continue this thing in the current setting or offline?
Offline, yes. I don't want to derail your talk, sorry.
No, it's not a question of derailing. I mean, from my perspective, this is wonderful to be able to have this back and forth. So there are a number of predictions. These are all in print. And for the sake of the fact that this is already 56 minutes past the hours, I want to.
Sorry to interrupt. This is Martin van Kerkwijk here. I wanted to ask you before you move on to cosmology, whether you see any links between these bursts and the Crab giant pulses, which certainly share the bending. They don't quite share the frequency structure, but they have similar banded structure. And
No,
I think
and
most people would place them on the outside of the magnetosphere.
No,
That's partly why I asked.
I hear you. I got it. I got your question. Even in the first few words that you mentioned, I understood your question. Answer is no. And the reason is, let me just give you the main reason. The biggest giant JP that we see from Crab and other pulsars, if you look at the luminosity of the biggest GP, that is about a few percent of the spin down luminosity, okay? And the FRB luminosity that we see is almost certainly orders of magnitude larger than the spin down luminosity. So at some very basic level, there is a difference. At a very basic physical level, there is a difference between the giant pulses and the FRB.
Okay, thank you.
And again, I'm happy to discuss this at length. So cosmology, and I am afraid you have to decide, meaning you please tell me whether this is something that I should just not talk, meaning should I just stop now and just skip this part completely? Or should I say in few minutes, should I take few more minutes or should I stop now? So I'm just asking for guidance here.
So I think safe to say that let's say that if you can wrap this up in about 10 minutes, I think this will be reasonable.
Oh, less than 10 minutes. I can go faster. Of course, that means that the clarity may be lacking, but the main point I would like to convey is the following, that FRBs, first point is that they should be there during the reionization epoch, meaning redshift greater than 6. And there are arguments that I will just point out, some basic arguments. And the basic arguments is that the universe was reionized by UV photons from massive stars, and some fraction of the massive stars die and produce neutron stars and black holes. And a good fraction of the massive stars at low redshift are magnetars. Furthermore, proof of the concept is that we see GRBs at high redshift greater than 6. There is one at 9.4. So we know that there is a channel of massive stars dying and leaving behind a magnetar or a stellar mass black hole endowed with a very strong magnetic field, because that is what is needed for producing the relativistic outflow and the jet in the GRBs. So this slide is simply making the point that magnetars should be there at high redshift during reionization. And they should burst. They should produce these fast radio bursts. And therefore, question is, can we detect them? This slide makes the point that we should. Of the 9 FRBs with known redshift, 40% of them will be detected during the reionization epoch if the threshold for telescope is in the radio astronomers unit 0.1 Jansky millisecond. And with a threshold of 1 Jansky millisecond, we should see 20% of the FRBs. Local FRBs, nearby FRBs would be detectable too during the reionization. You have all seen this before. Very simple concept of how FRBs can be used to investigate the epoch of reionization. And the simple concept is that you find more and more FRBs and larger distances through the reionization epoch and before the reionization epoch, meaning when the universe was neutral, you see the electron column density, which is the DM, will increase, and then at larger distances, when you are in the epoch, when the universe was neutral, there is no increase to the column density of electrons. So there is a maximum DM that you will have for the FRB. So very simple concept of DM max that you will see from a sample, from a catalog of FRBs extending to high redshift. And that maximum is dependent on the reionization history. And so this is here in the left panel, I showed two different reionization history. One, those of you who work in the reionization know this paper, Robertson et al., taken from observations of Lyman alpha galaxies and so on and so forth, crude model. And this dotted line is a different history, made up model. The point is that they have different DM max for the FRBs, these two different reionization histories. And that's one way that you can tell, you can investigate the reionization. There are complications. The IgM is fluctuating. The host galaxy of the FRB contributes to the column density. So we have taken that into consideration in this paper that we is coming out soon, combining that with fire simulations. The point is that you can combine all that. What you find is that if the DM max can be determined to about within 500, then you can beat the Planck 2020 measurement, which is providing information about the Thomson scattering optical depth, right, for electrons. You can improve on the Planck measurement from using the FRBs. This is the really very last slide. There are other ways of doing it without knowing the redshift. The previous method that I mentioned makes no use of the redshift of the FRBs. This is another way that you can simply bin the FRBs in the DM bins and have a way of exploring the different reionization history. Let me stop here. I have gone over time, and my apologies for having gone a little bit over time. I really do thank you for your patience, and I would love to get questions, critical ones, particularly comments, anything. So with that, thank you.
So on behalf of all CITA, let me thank you, Pawan, for a great talk. And we'll be taking questions from the audience. There's been quite a few during the talk, but if there are any more, then you're welcome to ask. So JJ, go ahead.
Oh, so your proposal with the shear waves exciting the Alfven waves is very interesting. So what's the main reason that you're invoking shear waves in the crust in the first place? Do you need to excite an Alfven wave to go across
Right.
magnetic field lines in order to have the two-pair instability work? Is that the
Yeah.
idea? Okay.
Yeah, that's right.
Okay. And then how much work has gone into understanding the coupling between the crust driving shear waves and the magnetic field in the magnetosphere? Is there a lot? Chris, I think, is also.
Yeah, there has been work. There was a recent work, recent as in a few months ago. It may have well be actually 5-6 months ago. There was a work done by Levine, was one of the authors. Biloborodov was another author. 3 people from Columbia, and I'm sorry, I'm forgetting the name of the lead author. The first author, I can look up the name, but if you search, they have looked at this thing. And so this is the most recent example that comes to mind, but there is a history of this thing. And the earliest, so I mentioned you the most recent one. Let me mention to you one of the earliest one. And that was, that is a very nice paper done by Blandford, Blaze, and Goldreich, 89, 88. So yes, and then of course, in between, many works. Chris Thompson can tell you all about it. Of course, Chris Thompson can tell you all about almost everything that I have told you.
Thank you very much. That was that. Yeah, thank you.
Okay, Shinyu, you raised your hand. Go ahead.
Yeah. Hi, Professor Kumar. Yeah, just about this alpha wave moving along those open field lines. So not only apart from this, whether the charge starvation can take place is a problem. So because this open field line still has some curvature, the alpha wave itself will be able to convert to some kind of fast wave, which will expand spherically even before what you call the charge starvation can take place somewhere. I mean, such kind of effect is not taken into consideration in your argument, right?
Yes, it is not taken into. So remind me, what is the time scale and the requirement on the plasma frequency for this conversion? Do you remember that offhand?
No, even you don't have this, as long as the plasma frequency is much larger than the wave frequency.
So it is larger. Yes, it is larger.
Yeah.
But only larger by a factor of a few to maybe 10. It is not much larger. And so omega p over omega, we are talking about is maybe something on the order of 10.
I'm saying like just even very close to the neutron star surface, just during the very early stage of this alpha wave propagation.
Yes.
Because I mean, such simulation has never been done on the open field line, but in the closed field line, you can clearly see that these alpha waves can get up very fast during the small conversion because of the curved background magnetic field lines.
That's right. That's right. So it's a quantitative thing that I would like to understand. As we were talking earlier today, this is something that, I am looking forward to talking with you in some more detail to try to, understand things more quantitatively, to see what how important the effect is, what the conversion time scale is. And so I don't have a quantitative, certainly, number and answer to provide at this time.
Sure, thank you.
Okay, Professor Jeremy Hill, go ahead.
Hi, Pawan. I'm going to be a bit contrarian in that, I think, well, FRBs coming from magnetars is maybe the most likely, but also the least interesting of the possibilities.
Jeremy, can I say something? Jeremy, can I say something?
Yes.
I totally agree with you. That is to say, I would love for these FRBs to what I call personally to be the Thomson magnetic nuggets. That's what I would love for them to be. Okay, but with that, go ahead. Yes, they are the most.
Yeah, so
Yes.
I mean, to a certain extent, it becomes almost, or maybe it is a key to understanding how pulsars make their radio emission. It's such a small fraction of the energy budget, but it's still kind of amazing how you get this coherent emission. But on the other hand, could there be, if we look at the history of GRBs, they turned out to be three different things. One of this, which is magnetars, if you think of soft gamma repeaters as a type of gamma ray burst, and then they repeat. But could there be other possibilities for FRBs still out there, or does this idea sort of account for every single one? Or can you find ones that we already know about that don't fit in this picture?
So I would say that it would be very foolish, certainly of me, to say that that the FRB population is one homogeneous population, meaning they are the same thing, coming from the same class of progenitor. I think the data that we have up to this point doesn't require there to be two different populations. Although there are maybe hints that maybe there is some difference between the repeaters and non-repeaters. But at this point in time, it's just a hint. It's not a very, very strong case to be made that we are dealing with two different populations. That's my view.
And then we'll see what happens.
Yes, see what happens. We will have a lot more bursts. And already we have got, when the Chime catalog comes out, we will have already something approaching 1,000 birds, and maybe we will see, maybe that will provide some answer to this thing. One population, multiple populations. So
Yeah.
we will know.
I'm holding
soon.
out hope that it's not just magnetars.
I hope so
But-
too. I totally, as in the terms of the excitement, it would be really exciting to find a completely different object, class of objects, producing these outbursts. So I'm with you. I agree.
Great. Thank you.
Right. So if there are no more questions, let's thank Pawan again. And this concludes the official part of the seminar. I'm going to leave the session open. So if anyone wants to stick around and talk more with the speaker.
Remind me, what's on Pawan's schedule next? Is there somebody?
No, so the next hour is reserved. The next hour is free. And
Oh,
I
just
think-
casual continued discussions. Excellent.
Yeah, that's my understanding.